right, what's up? I'm going to be showing you the proof of the quadratic formula. So we've been dealing with the quadratic formula since what, 7th, 8th grade now. I mean, we've been factoring for forever. But as always, like every single math class you have, they just throw equations at you and they don't explain why or how or why we should use them. So I think it's pretty interesting to show the geometry behind the quadratic formula. So that's what we're going to do. So if you recall, I'll put that in. So if you recall, this is the general form of a quadratic equation equals 0, right? We need to find the roots. So if you recall from, probably not because it was 5 years ago now at this point, in 7th grade we learned completing the square. That's exactly what we're going to be doing here. So if you see here, first let's put it in the standard form. X squared plus b over a equals 0. All right, cool. Now we are going to set just the parts with the x in them equal to this. All right. So you're probably asking, where are the squares? Where's the geometry? We'll do it. So here we have x squared. So it's literally just a square with two x's as the sides, x squared. Here you have a rectangular shape. I know it doesn't look like a rectangle, neither does the square. You have BA times x, because this will be the same length, all right? And then here we also have another rectangle of some sort. Doesn't matter, negative area, doesn't matter. Don't worry about that. So here, if we split this in two, we can actually turn it into an incomplete square with those two rectangles. When you split into, of course, this will be b over 2a, b over 2a, and then of course you have x here. We already know that because we have x there. So if you notice, we have this little gap right there. You know what we're going to do? We're going to complete the square. So that's where this whole thing comes from. If you notice, and if you look, this square is equal to b over 2a squared, all right? So now we're basically going to do exactly what we do when we complete the square normally, and we're going to write it as this. As you notice, this is what it'll be equal to when we complete the square. So now we can write our equation as x plus b over 2a squared equals, don't forget this part, negative c over a plus this. All right? So you see that and you're like, that doesn't look like the quadratic formula at all. You're right. We're going to try and simplify it and see if we can get something that looks a little bit more like it. So this is a bit of a process, but I'll try to do it as quickly as possible. I don't think I need to explain the algebra. So just watch what I do. B squared or a squared. I distributed the square. So if we add these up by using common denominators, we will get b squared minus 4ac over 4a squared. Now that looks pretty familiar, so we got to keep going. That's a good sign. All right, let's find the square root of both sides since we're solving for x. X is b 2a equals the square root of b squared minus 4ac over 2a. What I did was distribute it to the numerator and the denominator. That looks extremely familiar. So now all we do is solve for x. And that gives us, here, let's put it, you see this right here? Let's put it right here. Of course, this is plus or minus, by the way. We get negative b plus or minus the square root of b squared minus 4ac over 2a. And that is how you get the quadratic formula, and that's how they found this out. It's been probably hundreds of years ago they found this out. Right there. Pretty cool stuff. So, one of the questions that you ask always in every math class, any class in general, why are we learning this? Why do we do this? Well, I don't really think I need to explain what we could use this for mathematically, obviously, if we have a polynomial that is to the power of 2, we can find the roots, even imaginary ones. I'm not going to get into imaginary numbers here, that proof is kind of insane. But let's apply it to a real world scenario. So, I took chemistry 2 last semester. It was traumatic. But we get to use the quadratic formula several times in equilibrium reactions. What's an equilibrium reaction? Basically a reaction that goes both ways. Not that important, but let's say we have an acid of some sort, one with a single proton. And it disassociates in water to an ion, to a proton, plus the anion, all right? What we do, if we're given a K constant, which we are here in this scenario, Kc equals 2.0 times 10 to the negative 5. What's a K constant? Basically, it applies to an equilibrium. You can find concentrations with it. That's what we're going to do. Let's say you're given a 0.5 molar starting point of acid. We can use these two things to find out the concentrations of these at equilibrium. So that's what we're going to do. We start with 0 on both of these. You're going to be adding x. You're going to be subtracting x. So that means our concentration at equilibrium is 0.5 molarity minus x, and x. So given this, we actually have an equation that we can solve. K constant is equal to concentration of products, which in this case is H and A, over reactants, which here is HA. So let's plug in. We have Kc equals x squared over 0.5 minus x. What is Kc equal to? Oh, we put it up here. 2.0 times 10 to the negative 5. All right, I don't know if you can see that. Either way, this is the equation we're going to solve. If we solve for x, we will end up getting a quadratic of x squared plus 2.0 times 10 to the negative 5x minus 10 to the negative 5. Now, you could factor that, I guess, if you were really smart, but what we typically use here is the quadratic formula. It's a surefire way to do it. So, plugging it into the quadratic formula, I have it written here so we don't have to go through that mess. We have negative b plus or minus the square root of 2. This e right here means to the power of 10, or 10 to the power of negative 5. Squared minus 4, a is 1. 10 to the negative 5, which is c. We have here over 2, because a is 1. If you go through all this trouble, you do everything, you can then find that our x, using the quadratic formula, is equal to 3.2 times 10 to the negative 3 molar. So what does that mean? Well, that means our concentration of anions and protons is equal to this at equilibrium. That's pretty powerful stuff. And here we can find how much is left of our reactant equilibrium. That would be 1.5 minus 3.2 times 10 to the negative 3. And that is equal to, if I wrote it down, about 0.4968 molar. Not a substantial change, obviously, but this is a very simple example I could show on the board. So this is just one of the many applications that we can use the quadratic formula for. It's an extremely important thing. It's a very interesting thing, I think, especially the proof. We normally don't think of equations as geometric. We normally don't apply geometry to them. That's exactly what you do here in order to use the quadratic formula. So yeah, that's a little bit about the quadratic formula. Hope you enjoyed it. Bye.